If you are someone living in the 21st century, chances are you have already encountered an identification number once, twice, or most probably a lot of times. Might it be the EAN13 or UPC you saw on the packaging of the product you purchased from the grocery store? The number you found on your credit card? Or perhaps the ISBN you found at the back of your favorite book? For sure, there are times you are wondering, what are these seemingly random numbers used for? Well, as its name suggests, these codes are simply used to identify a specific product or account. But how does it work? Let's say you're in a supermarket and the cashier have the code on the product you purchased scanned. After scanning, the computer will then decode the data, and finding no error in it, the computer will then bring the data into a database where the information of all the products being sold in the supermarket are stored. Within the database, the computer will then find the set of information that matches the input identification code, and once found, the matching information is shown as an output, which could be in the form of price or product name. However, what if these codes have error in them? Let's say a single digit is replaced as a different digit, or two adjacent digits are transposed. Of course, we don't want that to happen because that could lead to very unwanted consequences. That could be a purchase of a wrong product, a transfer to a wrong account, or not finding the information of a specific good you are trying to buy. Thankfully, computers where these codes are being input have the ability not just to decode them, but to validate them as well. But how? That is through the checked digit systems built within them. These systems are algorithms used to validate the correctness of an identification number, and amazingly, these are commonly based on modular arithmetic. Unfortunately, there is no single system that can detect errors in all kinds of identification number. Different codes require different systems. Two commonly known and used systems are the Loon algorithm and EAN13 scheme that are used to validate credit card numbers and retail goods respectively. Now, having said that these systems involve modular arithmetic, we firstly have to know what modular arithmetic is.
Modular arithmetic is the process where numbers wrap around when they reach a certain value known as modulus. Imagine a face of a clock with 12 replaced as 0. You know that if its hands continue to rotate beyond 0, it will be back again at 1, then at 2, and so on. That is where wrapping around happens. This is the concept of modular arithmetic where 12 is the modulus. When we say 13 modulo 12, that is 1 since 13 is located at the same place as 1. Now, 14 modulo 12 is 2 since 14 is at the same place as 2, and so on. To put it even more convenient, when we are dealing with modular arithmetic operation, we basically want to know the remainder when a value is divided by the modulus. When we say 13 modulo 12, we simply want to know the remainder when 13 is divided by the modulus 12. If we do this, we know that the remainder is 1. Hence, 13 modulo 12 is 1.
Now that we are familiar to modular arithmetic, we now go back to the checked digit systems. How does a computer validate the code? For instance, say you want to buy a CD with this EAN13 code at the back of its case. The code is then scanned. After scanning, the computer then decodes and validates it using a checked digit system called EAN13 scheme. First, the computer temporarily disregards the checked digit, then multiply a weight of 1 and 3, two digits in the odd and even position respectively. The resulting weighted values are then added. The sum from this addition will now be added to the checked digit. Afterwards, the computer gets the value of the resulting sum modulo 10. Now, the rule is, if the final value is 0, then the code is valid, otherwise, it is not. Thus, from the example, the computer will know that the scanned code is indeed valid, and will now proceed to the database and find the information that matches it. Now, what if the transmission error occurs in EAN13 code? Let's say, from this, it becomes this, where 70 is mistyped as 17. Now, the computer will carry out the same algorithm from the previous example. However, due to different values, the final value does not equal to 0. In this case, the computer will know that the code is invalid, so instead of proceeding to the database, it will just let the encoder, in this case, the cashier, know that the code is invalid. And that's how the scanners through computers validate the code. However, EAN13 scheme is only one of the various algorithms that computers use to detect errors. There are actually more systems out there with varying uses, such as the Luan algorithm for credit cards, ISBN 10 scheme, UPC scheme, and many more.
Indeed, we can see that modular arithmetic plays an important role in the field of checked digit systems. However, it is only one of its various applications. In fact, modular arithmetic also plays a vital role in other fields such as cryptography, computer science, and music theory. Finally, in the rise of digital era, number theory and its cornerstone modular arithmetic is undeniably a tool of the humanity to build a more efficient, convenient, and secure world.